So first, thank you, Ellen and Gadir, for inviting me to speak with all of you. I have spent the last 15 years studying mathematics and statistics, and I just want to share a little bit of what I've learned, both in studying and working as a statistical consultant with a lot of social scientists. I also want to thank all of our Carnegie interns for taking that little survey that I sent out to all of you. I really wanted to try to gauge what you knew, what you wanted to know, and what might be most useful. If I've gotten that wrong, please let me know. We have 2 more of these sessions, and I don't want to put in a lot of work for things you don't want to hear. So feel free to give me your feedback at any point during the session. Another point of business, I don't think I have an hour and a half of material or even an hour of material to cover, but I wanted to make sure that we had enough time for really good discussion. So interrupt, right? This isn't like a course lecture. This is really, especially this first session, is kind of just a compilation of things that I think often get missed in maybe a first course in quantitative methods, and things that if you think about them a little more might make your life a little bit easier, okay? So if you have questions, let me know. Otherwise, I'm just going to kind of keep trucking to the end. Okay. All good. All right. So as Ellen said, this is the first of 3 sessions. And I believe that it's only fair that if you have to listen to a person, that they have to tell you a little bit about themselves. So my name is Erica Metheney. I am originally from the United States. I did a degree in theoretical math at SIUE. I then did a PhD in statistics at Texas A&M, where I wrote a dissertation about complex networks, which is not what I do anymore. After I graduated, I moved to Sweden so that I could be the statistician and head of the data team at GLD. During my time here, most of my work has been centered around surveys, household surveys, telephone surveys, web-based surveys, you name it, we've tried it. Ellen also mentioned that I am now the organizer of GLD's education stream, Learn with GLD. And our goal for that is to try to make ready-to-use educational materials for teachers, but also things just for regular researchers and everyday citizens. When I'm not dealing with data, which is not so often, I like to watch movies, I practice speaking Italian, and I spend time with my dog, Willow. I always integrate her into all of my talks, and she will actually come back around in a little bit. So that's a bit about my background and where I'm coming from today. So let's see. I named this session Quantitative Literacy because I didn't want to spend any time going through mathematical definitions or formulas or code or even real instruction on how to do things. I really wanted to focus on being able to think through these types of problems well. And I think this has a lot of benefits, and I want to go through some of those now. So this is a screenshot of the centerfold of The Nation, which is, I think, the largest newspaper in Malawi. And what you see are some infographics that GLD made representing data that we collected from our COVID-19 panel survey. And that survey collected data about how much knowledge did citizens have about the pandemic? How afraid were they? What types of struggles were they encountering? What types of preventive measures were they taking? How were they feeling about the authority figures who were imposing rules upon them? And we were able to take out the entire centerfold spread of this massive newspaper to convey this information to policymakers who would see it in the news, but also everyday citizens. But the effectiveness of this whole attempt rided on the fact that the audience could do 3 things. 1, they could read it, right? They could see and know how to interpret these graphs. If they know how to read the graph, do they know what it really means, right? And if they know what it means, should they trust it, right? Often these messages are coming from people, everyday citizen in Malawi doesn't know what GLD is. So can I interpret it? Do I know what that actually means? And do I trust it? And to me, that's the heart of quantitative literacy, is the ability to do these 3 things, to engage and to be able to assess of whether or not you should believe what you're being shown. But I also think quantitative literacy extends outside of research and your professional life. So This is actually a screenshot of the abstract of a paper I read a few years ago. And it happened after I thought I was being conned by my veterinarian. A veterinarian told me that the type of vaccine that I was giving my dog every year was subpar. It wasn't the right kind. There was this new method and I should switch. And I didn't know this person. We were new clients. And I was like, I feel like I might be getting played. And so I decided, hey, you know what? I have experimental design training, right? I have a certain level of quantitative literacy. What if I just read the paper? What if I just read the results and made my own decision instead of being reliant on some mediator that I don't know and I don't know how much I can trust? This can happen for all sorts of things, right? When you're reading about the performance of, I don't know, a new dishwasher or a washing machine, there are tons of places in life where if you have a certain level of quantitative literacy, you can be a more informed consumer. This would also apply to being a more informed citizen, reading reports from different organizations or research institutions. So being quantitatively literate, I think, means, one, having a good understanding of the philosophy behind it. It's not a set of rules or processes, but it's truly how we think about the thing. And for me, I think that the chief economist, Hal Varian, did an incredible job of describing what working with data is like. He said, I keep saying the sexy job in the next 10 years will be statisticians. The ability to take data, to be able to understand it, to process it, extract value from it, visualize it, communicate it. That's going to be a hugely important skill set in the next decades. This quote is from 2009. We're more than a decade out, and I think we would pretty much all agree that Hal was right. We live in a data age. You can't kind of try to go get information about anything without running into some statistic or data of some kind. But what I love about his quote is if you break down all the verbs in it, you actually see that the skill set that he just calls statistics is incredibly diverse. We have a lot of social components. We have a lot of computational components and then separately mathematical components. And to me, what this means is that no matter your skill set, no matter your interest, there is a space for you to engage with quantitative data and quantitative methods. So if you're someone who is very qualitative and you're like, this is not for me, I would argue that that's probably not true. You may just not be interested in the whole thing, and that's okay. My favorite quote, maybe of all time, is from the cartoon Rick and Morty, where Rick tells his grandson, sometimes science is more art than science. A lot of people don't get that. And I love this. I don't think I ever had a single professor who didn't actually say something like this. Statistics is an art and a science, and you have to be a master of both. So what does that mean? So the science is the formulas, the mathematics, the code that you write, all of those things that you would get out of a book or expect to be taught if you took a class. And those things are important if you want to do the work. But the art matters too, right? The art is how you make certain assumptions, how you make certain choices, how you design graphs. All of these things come together to convey a particular type of message and affect how you read the messages that other people are trying to send to you. And just like art isn't something you can learn from a book, right? If we think about like true artists, of painters, of how they actually learn, right? One, they learn by doing. You can't just read it in a book and say, I'm ready, right? You have to see and try lots of things. You have to look at other artists and see how they view things, how the techniques that they use, the choices they make. And it's exactly the same for quantitative methods. And so in these three series, I really want to focus on the art, how we view things, how we think about them, and how we develop the intuition behind them. And we're going to try to leave the science kind of completely to the wayside, because there are so many tools today to help you learn that stuff. And they were designed by people much more experienced than me. So I'm going to leave that to them. So what I want to show you now is how I think about statistical processes or quantitative methods. No, this is not truth. This is my kind of artistic perspective, okay? So for me, everything starts with a population, okay? This is just some group of individuals. That could be all citizens in a nation. It could be all voting age people in a certain district, all children, all youth, what have you. And I have some research question about those individuals. And this is one of the first things in my philosophy on quantitative methods that's so important, which is the research question, the question I want to answer, lives in the population realm, right? The population is the big, full, messy, complex, ugly world, right? And in a perfect world, I would be able to answer my question by surveying the entire population or measuring the entire population and just computing the answer. But we know that doesn't work. So we have to take a sample, right? I can get my hands on some of them. And the idea with this sample is to kind of create a proxy or an approximation of the population world. And there's a lot of science behind how to do that well. We're not going to talk about that today, but that's my goal, right? I want to take a sample from the population in such a way that this small sample I can manage, that I can somewhat control, is somehow related to the population in a meaningful way. But the second I take the sample, my entire worldview has to switch, because now I'm no longer in population world. I'm in sample world. This means I don't have individuals, I have subjects. These people have been chosen, they have been selected, they are now special in some way. And now that I have them, I can give them surveys, I can collect data about them, I could interview them, what have you. And now that I have all this data about this little subset of my population, I can start computing summary statistics. So maybe a sample average, right? Or a sample proportion, something like that. And the thing to remember there is that that single number, say that sample proportion of people who were afraid of COVID-19, that number lives in the sample world. It only gives me information about them by itself, right? That number came from this little tiny world and it tells me something only about the sample. So I can't stop here. If I stop with summary statistics alone, I've abandoned my research question over in the population world. And so I need something to bring me back. And that's where I need to take my estimates and apply some statistical inference to them. So these would be your hypothesis tests, your confidence intervals, all of those things. And that is the path when I think of quantitative methods that I'm taking, right? I start in the population, identify who the individuals are. What is my question? What people can I actually get my hands on to collect data from? What do I know about my sample? And then what can statistics tell me when I would try to go back? I heard once someone say that statistics is the science of learning from data. And I think that is a beautiful and very important way to think about statistics. Occasionally, you'll hear people talk about it as extracting truth. And I don't think that works because statistics is something we use when the information we have is limited. We can't look at the whole population. And it's variable, which could come from a lot of places. It just could mean people are different from other people. It could mean that we have imperfect measurement, right? When we try to measure a certain quality. So the idea of ever being able to get to truth, I think is too high a bar. I don't think that should be our goal. But if we set the goal to be, I want to learn something, and I want to know how much I can learn from my data and how much I can trust what I'm learning. And that's my personal philosophical view of how this works. A caveat, this is a very, what's called a frequentist view of how statistics work. There's another realm of philosophy called Bayesian statistics. I was not trained by Bayesians. I would not call myself a Bayesian statistician. If you're interested in that, I can send you resources to something else. But that is not my realm of expertise. But this is how I like to think about statistics, is how do I move back and forth between the population world and the sample world? So I hope I've convinced you that quantitative literacy could be valuable, right? Whether it's you want to save money, you don't want to be conned, or you want to be a more effective researcher, I think that there really is a space for all of us to increase this skill set to make us just more responsible and more informed citizens and consumers. So the first step towards quantitative literacy, I think, is learning to be comfortable around data and learning how to, what I call, become friends with data. And the first way we do that is through summarizing data. So if someone handed you a giant Excel sheet, You might say thank you, but it doesn't have any immediate value, right? You can't look at it and say, aha, I see the insight here. It doesn't work. So you need to be able to get summaries of your data. But before you can do that, one of the most critical skills you can have if you want to start working in quantitative methods is the ability to identify what type of quantitative data you have. So broadly, quantitative data comes in two flavors: numeric data, things that are numbers, and categorical data, things that put things into categories. But numeric data comes in two subflavors: continuous variables, things that you can measure as a fraction, say speed, height, age even, or discrete things, things that you can count on your fingers, how many children are in a household, that type of thing. Categorical data also comes in different subflavors. So we have nominal categorical variables, which just stick labels on the respondents, but the labels have no relationship to each other. They're just simply groups, as opposed to ordinal variables, where we're still labeling the respondents into groups, but the groups have some intrinsic natural order. So this would be something maybe like education level, right? So you have no schooling, primary school only, secondary, post-secondary. There's some intrinsic and natural order to these things. And the reason we have to be able to do this is because this is the key to unlocking every decision you're going to have to make from that point on. Knowing your data type will tell you what types of summaries you can do, what types of graphs you can use, what types of hypothesis tests you can do. It is the deciding factor for pretty much every single decision. So we need to be able to feel confident in that. So let's look at a few numeric summaries. These might be things, if you've taken quantitative methods, you probably know these things, and that's okay. I'm just trying to do it for completeness so that we can all be on the same page for our next sessions, okay? So for numeric variables, imagine you have an Excel sheet, you have a column of numbers. What are the things I want to know about that variable? The first, I want to know something about its shape. And shape is something that we get from histograms. And there's two qualities that we use to describe the shape of a numeric variable. The first is its modality, where we're trying to understand where kind of the most common observations are. And you can have any number of modes you want. If you have one mode, we call that unimodal. You have this kind of one hump here. It could be bimodal, where you have these two groups, or you may have no groups at all, and we call that uniform. You could also have trimodal, quadmodal, but that's pretty uncommon. The other thing that you may have heard of is something called skewness. Some people call this the slantiness of the data, right? You have three options for skewness. One is symmetric, which means you have some most common value, and then it just kind of trickles away as you get further away from that most common value. And then you have right and left skewed. So for right skewed, most of your observations fall on the low end of the range, but you have a few quite large observations as well. And left skewed is the reverse of that. Some people have a hard time remembering which one's left skewed and which one's right skewed. I was taught, if you imagine that this is a slide and you put a little person at the top, whichever direction they will go, that's which skew it is. So I put a little man up here, he slides down to the right, so it's right skewed. These are things you probably would have seen in a first course in quantitative methods, but what you might not have been told is how to feel when you see these things. So the golden standard, the most perfect thing you could ever find when looking at the shape of a value, is a unimodal symmetric shape. And the reason for that is things that are unimodal and symmetric behave nicely with all the big theoretical mathematics that are running the statistical machine. It makes life easy. Now, that doesn't mean that if your data is skewed or multimodal that you can't do anything, but it might mean you're more likely to run into problems. However, things like skewness tend to matter less when you have big sample sizes for a lot of things. And in the modern age, I don't know the last time I saw a data set that had such a low sample size, I would be worried. But if you do find yourself concerned, there are methods to handle that. So it is something to keep an eye on. If someone has a numerical variable that they're talking to you about, and they don't tell you about the skewness, especially if they have a small sample size, you might be concerned and want to ask about that. The other thing that's very important and something that gets overlooked all the time is unusual observations. Sometimes we call these outliers. Some people call them influential points. And I once had a professor say, you know what it means when something has a lot of names, right? It means it's incredibly important and you need to pay attention because multiple people discovered the same thing without communicating to each other. And I think this definitely falls into that category of topics. The problem with outliers or influential points is that they are observations where when they're in your data set and when they're out of your data set, you draw very different conclusions, whether that's the graph looks very different, the hypothesis test has a different result, the model has different coefficients, whatever it is, you get something very different. And so that's a pretty serious problem, right? The bigger problem is there's actually no definition of what it means to be an outlier, what it means to be influential, or what it means to be unusual. And since there's no one definition of what it is, that means that there's no single test to see if your observations are unusual. There are a lot of tools to do this. One is the 1.5 IQR rule. If you've ever seen a box plot that has the dots at the end, those dots are dots because they kind of failed the IQR rule. In regression, we have something called Cook's distance that tries to quantify this. You could also use z-scores. I'm not going to go through the definitions of those, but the takeaway really is that there are lots of ways to check for unusual observations. And when you have them, it's very important you address it. So if you're reading a piece of quantitative work and someone has a numeric outcome and they have no mention of whether or not they checked for outliers, that's a place where you could push back. It should be something even as easy as no outliers detected. Totally sufficient. If they do say they have outliers, they should be very explicit about how they handled them. Did they throw them away? Did they build something into their model to make that a special case? Whatever. It's a good thing to keep an eye out for if you're ever trying to critically evaluate a piece of quantitative work. The other reason that this is so important is whether or not you have outliers is how you determine how you should measure the center of your variable. That would be like the most typical value that you should expect from that variable, and the variability around that typical value. So if you find yourself in a situation where you are not, you have no outliers, right? Everyone's pretty well contained, then you can go ahead and use the mean, the average, the thing that we would all expect, because the mean uses all of the data in its computation. So if there were outliers, it would be affected. But if there's not, you're totally okay. If you do have outliers or influential points, you might want to take the median, right? We can imagine if we took, I don't know, the average net worth of Amazon employees, we get very different results if we include Jeff Bezos or not, right? So we need to know if we have outliers so we know how to summarize our data in an effective and honest way. For variability, we also have options. If you have outliers, you could use this interquartile range, right? Because that ignores the top 25%, the bottom 25%, and just measures kind of what the middle of your data looks like. If you don't have outliers, go ahead and use standard deviation, the square root of the variance. It's totally fine. So this also really matters, right? People throw means around like they're nothing, right? But if someone hands you a mean, but they didn't tell you if they had an outlier, you should probably be a little bit suspicious. Okay, so that's numeric variables. There's a lot to learn there. Let's move to a categorical variable. Whether we're nominal or we're ordinal, to summarize that variable, we can get the count for each category. Okay, we can convert that to a percentage or to a proportion. The takeaway is it's boring. Categorical data, when it comes to data summaries, are remarkably boring. There's just not much you can do. However, there are a couple interesting points that you might be able to take away from very special types of categorical data. And this might be things you weren't taught in a first quantitative methods class. So the first is about ordinal variables. I've seen this a lot where someone has an ordinal variable, say education, like we talked about earlier, and they want to treat it as if it was a discrete numeric variable. So instead of having the categories no school, primary, secondary, post, they use it as 1, 2, 3, 4. or maybe 0, 1, 2, 3. And then now that it's numeric, we can take the average, we can compute a variance, we can do all those fun things that we were doing in the last slide, right? This can be a very informative and very helpful thing to do. However, it rides on a very strong assumption. When you look at the numbers 1 through 4, the difference between a 1 and a 2 is exactly the same as the difference between a 2 and a 3, and a 3 and a 4. If I replace my education categories with these numbers, I'm saying that the difference between these levels is also equal. That the difference between being someone who finishes primary school compared to having no schooling is exactly the same as someone who finishes post-secondary school compared to secondary school. And I don't think we'd have to work that hard to come up with an example where that's almost certainly not true, right? There might be much greater benefits, right? Or much bigger differences between going from one level of education to the next. So it might be actually that that's a much better represented by like 1, 4, 5, 9, right? Maybe it's not equidistant. And so my recommendation is if you find yourself in that situation, it's probably not a good candidate to put onto a numeric variable. So that's something to keep an eye out for. The other is if your categorical variable is binary or an indicator variable. So those are variables that take on the value 1 if an event occurs, and it's 0 if that event does not occur. And here, the proportion gives you an incredible, important piece of information. So if you compute the proportion of 1s, say, you can tell whether or not the event that you're talking about is rare. So in general, in statistics, we say that an event is rare if it occurs 10% or less of the time. Note the opposite of this is true. If the percentage of 1s is 90% or more, right? If either proportion is less than 10, we consider this a rare event problem. And the reason it's called a rare event problem is because a lot of the tools that we would use, like certain types of regression, are not going to perform well. There's just not enough of a signal from the small group to pick up anything, right? You just have this loud voice of the dominant group that's shouting so loudly, we can't hear anything. And in those cases, there is a ton of tools and methods that you can use, but you do need to use them. So again, this is another part if you're ever trying to critically evaluate a piece of work and you see someone who has a binary outcome variable, one, they should tell you the distribution of that binary variable. If they don't, maybe push back on that a little bit. Two, if they do, and that percentage is less than 10% or greater than 90%, and they don't talk about having a rare event problem or using a method to address it, that would also be a place where you should push back. So in general, data summaries are not so exciting for categorical variables, but there are some points where you could make some really big mistakes, or other people could make mistakes that could have pretty big consequences in what we're able to learn from our data. So the last point of data summaries is about correlation. So correlation is about trying to measure the association between two variables, all right? I pulled this directly from Wikipedia. And here on the top left, right, we have perfect correlation. Whatever value X takes on the X-axis, Y takes the exact same value. They move together perfectly, okay? If we go one graph over, it's a little bit weaker. Now we see that as X gets big, Y gets big. As Y gets small, X gets small. Generally, they follow each other pretty well. And we see as we move across that this relationship gets weaker and weaker until right in the middle, it's just completely random, right? It's just a big old blob sitting there. And those correlations make sense, right? The intuition, perfectly positively correlated to perfectly negatively correlated. But look at the bottom row. At the bottom row, if you ask yourself, is the X variable and the Y variable related? Does it seem that the value of X tells me something about the value of Y? I think we would all say, yes, definitely, right? This doesn't look like a random pattern, but the correlation is 0. The amount of the association is 0, and that's because what's being computed here is the Pearson correlation. If you've ever been taught correlation, this is almost certainly the correlation that you were taught. And the thing about Pearson correlation is it only looks for linear relationships. So this idea that if X goes up, Y goes up, or if Y goes down, X goes down, right? But we know that there are many relationships that exist in the world that are not linear in nature. And this bottom row is a great example of those types of nonlinear relationships. So the point I want you to take here is to remember that there are multiple types of correlation. And if someone just says correlation, they probably mean Pearson correlation. And it better be true that those things have a linear relationship. And a scatter plot like this is the fastest way to know if that's true. There are many other types of correlation. The most common you will see for nonlinear correlation would be Spearman's or Kendall's. I'm not going to show you how those work, but I want you to know that they exist. And they're really important when you start dealing with more complex or nuanced relationships. Okay. So I really only have one topic left, and I think it's the most fun part. And it's about graphs. I love graphs. I think they are one of the most important skills when it comes to quantitative literacy and also just doing research because it's important for articles and for dissemination. So why are graphs so important? I think they're important because they provide so much for us. Number one, we use graphs in order to become friends with our data. I remember one time I started a consulting project with one of my professors when I was doing my PhD, and we got the data in finally, and I was so excited, and I rushed to his office, and I was like, I don't know if I should use this model, or if I should use this model, or I should do this, I should do that. And he goes, whoa, whoa, whoa. I've never seen it before. Can you make me a graph? Can you show me? And I was like, what do you mean? We need to get to work. He's like, how could you possibly know the right thing to do to something you've never seen? So I like to think about it as when you get a new data set, you kind of need to become friends. You have to get to know each other. You need to know what problems it has, what limitations it has, all of these things. And graphs are the fastest way to get that information. Another reason we like to use graphs is for attention. If you think back, the first books all humans read are picture books. And if we're honest, adults are just big kids. And if you give people the choice between reading a block of text and looking at a pretty picture, they're going to choose the pretty picture every time, right? That's much more likely to get someone to stop scrolling through Twitter, right? Or if you imagine a policymaker with a stack of briefs on their desk, a beautiful figure could be enough to get them to just pause for half a second more. And that's one of the reasons we want to use them. And the other reason is we use graphs to tell stories, right? We have a narrative that we want to convey about our data to someone else. You may have heard the phrase, a picture is worth 1,000 words. That's true. And for quantitative data, I think very problematic, because what that means is maybe I make a picture, and when you read it, 500 words come to mind. When another person reads it, a different 100 words come to mind. I might not be conveying the same information. So the other reason we use a graph is to send a very specific message, okay? Sometimes we just want to show off our data and look how beautiful it is. But other times we have something very, very precise we want to say. And so what I want to go through now are some points about making graphs that I think are often underemphasized when we give students their first instruction on how to make graphs and figures. I want to show you some examples of classic graphs and things that can go wrong. I want to show you some figures you've maybe never seen before that are really good options to graph your data, and some resources to go ahead and use them, okay? So I think there are three things that are often missed when we teach people about graphs. The first is having a really serious discussion about color choice. When you need to use color, which we often do, is it a colorblind friendly palette? Is it a printer friendly palette? The general recommendation is that if it's possible, use patterns or shapes instead of colors, right? Then you don't have to worry about any of these issues. And this is a really good choice for things like journal articles. But if you're making a graph to get attention, say for a poster or in a newspaper, you're definitely going to want a little color. Imagine that first screenshot I showed you of the centerfold. If that was in black and white, it wouldn't be very appealing, right? It may honestly feel like kind of a slap in the face of just this big black gray wall of pictures. So something to keep in mind. And I will give you a resource to help you pick good color palettes at the end. The other thing is keeping a very careful eye on the size of the text in your figures. APA guidelines say generally no smaller than 8-point font, no bigger than 14. And on the same note, thinking about the resolution, at the end of the day, all of your graphs are images. And so they have a resolution. And it is recommended for pretty much everything to use 300 dpi. And I'm really passionate about these last two things because when you make a figure, you're inviting someone to come and spend their time looking at something. And it's not very kind to invite someone to look at something they can't actually see. Right? And it probably took you a lot of time and effort to make the thing. So you want to make sure that your message gets conveyed. And these last 2 points can go a really long way into making a better experience for your reader. Okay, the last thing I want to show you is honestly something I made up, and it's called the glance test. Okay, the glance test to me is the ultimate test for any graph I make. And the glance test says that with a quick glance, the reader should be able to, one, know if the message is simple or complex. This, especially in the research and policy sphere, is incredibly important because within an instant, I need my reader to know how much time they need to invest to really get my message. And you can signal this in a lot of ways. If you have a complex message, you may have a lot of legends. You may have arrows that point at things. You may have a really big caption where you're interpreting the graph for the reader. But what you don't want is to have a very complex message embedded in a figure and for your reader to kind of glance, think they get it, and then walk away with a completely different story than the one you were trying to convey. And I also say by the glance test that if the message is simple, it should be able to be received in its entirety with kind of a passing glance. Maybe the nuances get lost, but the main core of the message should be easily conveyed. So I want to play a little game with all of you. I'm going to open up the grid here, and I'm going to see how your glances work on some graphs. Everybody ready? All right. What was the point of that pie chart? What was the point? What did, yeah, Mariam.
What each like portion of data represents from the bigger picture?
Yeah, exactly. So that is like the definition of the pie chart, right? And it really didn't convey anything past, this is a pie chart, right? It did convey that message quickly. It showed that there are multiple kind of categories. It showed how many were in each category. It was a pie chart, 100%. But did it have a story to tell? Not so much. Okay. I've made an edit. I want to give you another glance. Tell me if you can see any story behind, past just I'm a pie chart. Okay. Was anyone able to see a story in that? Did anyone see more information that maybe they didn't see the first time?
Yeah, so, oh, sorry.
No, you're good. Yeah, no, shout out because I can't see all the faces anyway.
I was just gonna say I saw the number 4 on each chunk of the pie chart.
Yeah. So it was labeled this time. Exactly. There's more. Go ahead and shout. If you have hands up, just go ahead and shout. I can't see everyone.
I think there is only one number that different than the other. It's 6. So
Very
it says
nice.
that, yeah, everything is equal, and just this one is different.
100%.
Just this slice.
Yeah. So congratulations, you're a very fast reader. You were able to take all of them in. So let's think about that. That is exactly the story. There is only one group that is different than all the rest. Would you say that that's a simple message or a complex message?
No, I think it's pretty simple, actually.
Okay, so it's a simple message, but let's look at this graph and think about all of the steps that my reader has to take to get that message. 1, it's a pie chart. We have to start there. It sounds silly, but it's true. Then they have to say, okay, they're labeled. And they say, okay, they have to now read all of the numbers. They're in a circle. And we as humans are not taught to read in circles, right? So that's a lot of effort. So now they say, okay, the 6 is the only different one. The 6 is green. I go over to the legend. Green is C. C is special. That's a lot of work for a very simple message. So then the question becomes, can I do it better? And I say the answer is yes, because I could do something like this. Right? I instantly point the reader directly to the point I want to make, right? So I highlight just the wedge that pulls them right there. The only color, right, is the C. They don't have to read through the legend. They're pulled directly to the right label. And all of the other ones are exactly the same. So I just make them all the same color. So this is a fun example, I think, of the glance test and making sure that you've built your figure so that the effort to get the story out is proportional to how complex it is, right? I hate to tell you this, but most people are not going to look at your figures like they're in the Louvre standing in front of the Mona Lisa. It's not going to happen. They're not just going to sit there and adore it and take it in for all it's worth. You're lucky to get a glance, especially if you're trying to do something with policy. You imagine a policymaker with a stack of briefs on their desk. You only have a second. And so a little intentionality can go a really long way. I think this exercise, particularly this first one, also does a really good job of reminding us that humans are inherently untalented at assessing the differences of angles. It's just not something our brains are very good at. We can do it, but it's a lot of work. And so in general, pie charts are not good at easily conveying nuanced differences. Personally, I only like to use them for a couple messages. One group is special. 2, one group is dominant. So it's like when the pie chart is like one color, basically. Or when you have like there is no winner. So you have a pie that's divided into so many teeny tiny pieces that you don't have anything to see. If the idea is that, oh, this is slightly bigger than this, and it matters that it's this slice and this slice, the pie chart, it just makes you dizzy going round and round. No matter how well you label it, no matter how well you color it or shade it, it's just not, it's not going to work. So that's pie charts. Let's take a look at some other classics. Yeah. So let's take a walk through my graph gallery. Histograms, the most classic and simplest way to graph numeric data, right? So what does the histogram do? It just bins numeric observations into groups, right? Essentially, it makes numeric data categorical in some way. The big thing to remember on histograms when people send them to you is how wide they set their bins. Did they use the default from the software? Did they choose a different number? These are things you're going to want to know because here it's the exact same data. I've just varied the bin size. And the shape of this data changes drastically. We go from seeing maybe one mode, maybe uniform, right? To seeing probably 2 modes, very clearly 2 modes, whole bunch of garbage, right? So keep an eye on your bin size. What's fun with this bimodal distribution, when you see something bimodal, you may wonder why. Because bimodal sometimes is an indicator that there's kind of 2 processes happening at the same time, maybe subgroups or something like that. And I want to show you why this happens. I can isolate it perfectly. If I, instead of graphing this entire variable, if I graph it separately based on the geographical region it came from, and I create a density plot, I see this. So this is the exact same variable. I'm now doing density plots instead of histograms because I wanted to show you something else. And you see, we get very different behavior in these different regions. In Lilongwe, we really have a high preference for lower values, but there is a second mode of low values and higher values. Lusaka really trends to the high value side, Malawi border to the low. And as I stack these guys on top of each other, I get these kind of very interesting bimodal shapes. So if you ever see a multimodal histogram, the thing it should trigger in you is, where are they coming from, right? Can I identify the mechanism that is creating kind of these two very common or three very common responses? Density plots versus histograms. I don't have a feeling about this. In some ways, I think visually density plots are nicer just because they're smooth, right? Like it's a less bumpy ride for the eye. But that's not a scientific thing. That's very much an art comment, right? Follow your heart. They are essentially equivalent. Okay, now I want to talk about accidental / maybe intentional mistakes and ways that we can mislead people. So this is actually a graph from a paper that I am actually co-authoring with Ellen. And it is the most recent example of when I made a terrible, terrible mistake and I almost deceived my reader. So what we have here are 4 plots that show 4 different interaction effects. And the interaction is between whether or not I provided a respondent with an additional piece of information or not, and whether or not the respondent was co-ethnic with the candidate I was describing to them. And the y-axis here is the predicted likelihood that the respondent said they would vote for the person. So the y value should be between 0 and 1 because it's a probability. Don't worry about the details so much. So what we see here is when you have no information versus when you have information, in all 4 plots, you see a change, right? A nice steep slope. And they all look relatively similar, right? Like the predicted values look the same, it's all fine. Until you realize that the y-axes are not all the same, especially on these top 2. This dot and this dot seem, the top ones on the top row, look like they're the same value. Indeed, they're not. And that's very deceptive. And the reason this happened in this instance is I let my software by default choose the y-axis, right? And the software, all it's usually thinking is fill the space, fill the space, fill the space. It doesn't care how much it has to stretch or slide. It just doesn't want to leave a bunch of white space. And so since these were smaller than all their neighbors, it had to zoom in and pull it out. So that is clearly deceptive. And this happens all the time. Anytime you see 2 graphs that have the same y-axis side by side, like it's the same like value, make sure that the axes are the same. Because if someone isn't keeping an eye on it, the default settings of the software might lead you to an incorrect conclusion. So this opens up the big question of, okay, this is clearly wrong. What do I do? Okay. And I think this really sums up a lot of statistical questions. And the reality is almost always, there's never a right answer, like a single right answer. There is a very well-known list of wrong things. So I tell people that it's kind of like avoiding potholes when you drive. Like you're not trying to stay on the road. You're just trying not to drive in the potholes. Okay. This is a pothole. We don't want to do this. So let's think through the other options. A very conservative approach would be to say, well, if the range for the y variable is from 0 to 1, I should put all my graphs on 0 to 1 because that is the most transparent, the most honest I can be for my reader. And that looks like this. Does anyone have feelings about this compared to this? It could be aesthetic, it could be scientific, it could be anything, any reactions at all.
In the first one, I don't know if that's like an observation that makes sense, but it
Sorry, could you repeat it? I didn't have sound. It was delayed a little bit for a second.
like graph image looks more flatter than the first one, and so it kind of makes it feel like there's not much data similar to the last one.
Yeah, that's one of the most serious problems, I think. These very steep lines that I had before now look very flat. And somehow that kind of makes it seem like I don't need to care. Like, okay, cute, you have an interaction. It's not doing anything, right? That is not the message that I want to give to my reader. Like, that's clearly wrong. Anything else? I mean, that's an incredibly good scientific observation. Any aesthetic observations? Just a lot of white space.
Yeah, I was gonna say.
Right, exactly. That's so much just empty desert of space. And if you have ever published an article, you know that page limits are serious business. I am taking up inches in my paper here for nothing. So those are two, I think, very good reasons to say, while this may be a conservative and transparent approach, it may not be a wise approach that serves me and my purpose. Okay, so, okay, I don't want to do this. I don't think this is wrong by any means. I just don't think it serves what we want to do. So I'm going to show you. Yeah, here's
I'm gonna ask, is it possible to like have a 0 to 1 but change the scale instead? So not have it go like 0.25?
Yeah, so to rescale the numbers or to crop it?
To rescale the numbers.
Yeah, so you could. And a statistician, I think, would likely say, absolutely. I think any social scientist would say no. My experience is that things like rescaling often make people a little nervous, because every time you manipulate the data one more time, people feel their intuition and their confidence drifting away, right? Because now they're like, well, what does a rescaled probability mean? And you're like, well, it's to look nice, you know? So the answer is definitely yes. I think that is scientifically a very good solution. I think it is socially one you would get a lot of resistance with. So very good suggestion. Definitely wouldn't do it. But if you ever find success, please let me know and tell me how you did it. Anything else? Any other questions, ideas, comments? I'm going to show you what we did. You don't have to like it. What I did is I just chose a range on the y-axis that covered all of the effects. So I ended up choosing 0.6 to 1. And I think this is nice. Here we can see that these numbers are much higher than the ones on the top right. We can see that there is some slope. They don't look super steep or anything. It's not so misleading. But here, this is not necessarily transparent in and of itself. You will need some supporting text or a caption. I think it would be important to have a note somewhere that says, hey, make sure you realize that the y-axis starts at 0.6 or something like that. Because it is nice, because when people, like we said, they're not spending hours looking at your plots, and we don't want to accidentally lead them the wrong way. So both of these, I think, are completely valid options. I think in the statistical community, you could get away with this. They would say, yeah, that's not a horizontal line. Those confidence intervals don't overlap. That's totally an important interaction. In other fields, you may get that's flat. I don't care. So you have to also know your audience and know what they will find impressive or important or acceptable. It's an unfortunate part, but that's the art. You have to know your audience a little bit. Okay, those are the classics. I didn't show you a bar chart because you've all been to school. I trust that you know bar charts. They have the same problem with scale that we just did with those line charts as well. I want to show you some of my favorite, what I think are lesser known graphs. The first one is called a lollipop chart. Lollipop charts are super cute. They're just bar charts that have been rebranded. So instead of having these big rectangles, you have a dot and a line. I think there's two reasons to do this. One is aesthetic and one is scientific. From an aesthetic point of view, when you have a whole bunch of groups like you have here, right, from A to Z, if those were rectangles, it would be visually very heavy, right? It would be like a fence if these were bars. And depending on how many graphs you have or how long the text is that you're reading, you might not want to do that to your reader, all right? Or if you have a whole bunch of bar charts, mix it up, make it fun. But from a more serious point of view, is when I think of a bar chart, I think of measuring something that accumulates. So imagine that you have a bar chart that shows the total amount of funding that was awarded to different topics in political science, right? So that height of the bar is the number of dollars. And it makes sense that if I add $1, if there's $1 more funding, it goes up by $1, right? There is this idea of a pile that's growing and growing and growing. But sometimes I want to plot a numeric value that doesn't have this intuitive idea of accumulation. So imagine instead you wanted to make a plot of, say, the average amount of funding per project, per topic, all right? So I don't just want to know the total amount of money that's awarded, I want to know how much money people actually get per grant. And in that case, my dot would be where the mean is for that group. And if it was a bar, the idea of adding one mean unit doesn't have the same idea, right? Of there is a stack and I just keep adding to the stack. It's a kind of a more distinct point. And the lollipop does exactly that. It makes it a point. So that is, again, a very artistic thing. The bar chart is also correct. But to me, it matches more the intuition behind, am I accumulating something or am I just comparing different numbers to each other? Okay, the next one, this is my favorite plot. This is my favorite chart. That's a very nerdy thing to say, to have your favorite plot. But one of my career goals is that by the time I retire, every political science paper with categorical data has a Mosaic plot in it. I think this is the single most powerful, important graph for categorical data that is almost never taught. Have any of you ever heard of Mosaic Plot before? Have you seen one? Yeah, they're not, I don't know why, but I'm going to show you, I'm going to walk you through this very slowly and show you why this is the ultimate graph. So the whole point of the Mosaic Plot is to visually show the relationship between two categorical variables, all right? And I want to show you all the information I get. So here I have an example where I have one variable, which is the type of village the respondent lives in, rural, peri-urban, urban, peri-urban, or rural. And then I have what that person thinks is the most important thing in their village. So spiritual well-being, employment, land security, different types of things like that, okay? So a Mosaic plot is made up of tiles, hence mosaic, and the width and the height of the tiles are specified by the distribution of the two variables. So if we look at these red tiles at the bottom, the width of each tile is proportional to the number of observations in the data set that fall in that category. So the rural column here is the widest column, which means that most of our observations fall into the rural category, with fewer being peri-urban and fewer that are urban. And these two are close to the same. And the same thing works on the height of the tiles. So the heights of the tiles are proportional to the number of observations that fall into each category on the y-axis. So very quickly, we can say that in general, when we look at the most important variable, most people either mention spiritual well-being or employment. Very few people mention community relations or material assistance. So what that is that's the distribution of each of those variables separately. You could create 2 bar charts that show that. You could do a grouped bar chart too that put them side by side. But instead, we get it for free within our Mosaic plot. But that's just the bonus information. We're really here for the relationship between them. So to read to see if we have a relationship, we look at the white line between any 2 adjacent colors, and we see if that line is flat or whether it makes a stair-step pattern. If that line is flat, then there's no relationship between that category and the other variable, because the proportion of respondents who chose that answer is the same across the other levels. If, however, you have something like this, where we just have stairs and stairs and stairs all over our plot, that's very strong visual evidence that these 2 variables are related. So if we look at this, for example, the employment, we see that employment was a much more common response for people in urban areas than it was for people in rural areas. If we look at community relations, we see that's a much more popular choice in rural areas compared to urban areas. So if you've taken a quantitative methods class, you may have learned about the chi-squared test of independence. It's a hypothesis test for checking if 2 variables are related. If you don't know what that is, we'll talk about it next time, don't worry. But what's interesting is the Mosaic plot is essentially a visual representation of the mathematical computation behind that test. It's almost a perfect kind of one-to-one correspondence. So I love this. I don't think there is a faster way to analyze relationships between categorical variables. At GLD, we use these all the time. So when we get a new data set in, let's say we do a survey, or if someone shares a data set with us, the first thing you have to do is figure out where are the interesting things in my data set, right? Where, like, not everything's interesting, unfortunately. We worked hard on it, we paid a lot of money for it, but a lot of it's not going to be very interesting. So how can I know where to spend my time in my data set? And so what we do is I typically generate 600 to 800 pages of these. And by me, I mean, typically it's interns like Victor, who's here with us today. He had the pleasure of doing this once. And what we do is we take all of our demographic grouping variables, so gender, age, education, wealth, region, ethnic group, all of these things go into one set of variables. Then we have all of our other topic variables, like what's the most important thing? Were you afraid of COVID? How often do you wash your hands? These types of things. And we create a Mosaic plot for every pair of variables across these 2 groups. And then what's super nice is you may have 600 pages, but all you have to do is scroll through and see, where do I have more or less straight lines? And where do I have nice stair-step patterns? And very quickly, I could go through huge, huge surveys worth of data and know, okay, it's very likely that if I spend my time analyzing this pair of variables, I'm going to get something very exciting. All right. And that there's not evidence here. And it's also just a good record to have in case you have people who want to use your data in the future and they want to know, I don't know, what's going on and different things. So that's Mosaic Plot. Look it up, use it, tell your friends. They're great. I think it's the biggest bang for your buck when it comes to a graph. I've never gotten more information out of them. The last one, pretty uncommon to see in social science because we don't usually have continuous variables ever. But if you ever are lucky enough to find a continuous variable, a violin plot, particularly one with a box plot, I think is a beautiful way to show the distribution of your data. All the violin plot is, it's that density plot reflected across like a y-axis, which makes this kind of wobbly violin shape. That lets you see the modality of your data. And then you can overlay the box plot so you can check for outliers and things. This is just an aesthetic choice. You can get the exact same thing with a histogram and a box plot, or a density plot and a box plot. They're just pretty. It's just a pretty thing. And if you have to stare at hundreds and hundreds of graphs, it's a pretty good time. All right, so the last thing I have to share with you are just some resources to add to your toolbox. If you're interested in learning about what other types of graphs there are, because there are a lot of new types of graphs or graphs you've maybe never seen. I can't recommend the R graph gallery enough. It will also provide you all the R code you would need if you wanted to try to graph something in R. But it also, on a lot of the pages, has really short discussions about the pros and cons and strengths and weaknesses of these different graphs. And I just think it's really an incredible resource. I didn't tell you, but I am an R user as a statistician. That is my default. And I do believe that for journal articles, there is no better option than ggplot in R to make graphs. And that's because everything is customizable. It's essentially equivalent to drawing something by hand. That's the level of control that it gives you. And when you're trying to make sure your font is just right and your labels are just so, and you want to put an arrow to highlight something, you need that level of control, but it can be quite daunting to have that much freedom. But this YouTube video does a really good job of providing intuition behind the syntax and the code, which can be very overwhelming the first time you start working on something. I also want to share the Color Brewer 2 with you. This is an incredible website that will help you build color palettes. So you can tell it how many colors you need. You can tell it whether you need it to be colorblind or printer friendly, and you can choose whether what you want your kind of color range to be. If you want to be blues, orange, red, a heat map, rainbow, what have you. And you put all the settings in and it generates a palette for you without any problems at all. So I will make sure to post all of those links into your SharePoint website under today's lesson in the seminar series. So that's it for today. I'm hoping this was just like a really easy day that you're like, I knew basically all of these things. But the main takeaways I wanted to do was maybe share some things with you that may have been overlooked in your earlier classes or your earlier experiences, and really encourage you to start thinking about the art of quantitative methods and to not put so much pressure on yourself to focus on the science bit, but think about why we're doing them, how the whole process works, and how you view the process, right? And to think about, what is your artistic expression when it comes to quantitative things. Our next session will be much more kind of technical-ish. We're focusing on confidence intervals, hypothesis testing, statistical power, linear models, and really trying to develop the intuition behind those things and the ability to talk about them in a very accurate but casual way. Because I think when you can do that, it helps you write better and it helps you read what other people are doing, especially when maybe they're not writing very clearly about what they're doing. After that, the last week is going to be about critically examining different pieces. For that, if you want to bring some examples of things you've read that maybe confused you or didn't like, that's fine. I'll also bring some examples for that. But otherwise, that's all I had. I told you I didn't have a ton of material for today, but any general questions, anything you want to make sure we talk about in the next 2 weeks,